Dear student, so today I am going to deliver lecture 2 for the course Nonlinear Function Analysis and Application. So in the last lecture I discussed some basic definitions and results and some motivational and interesting fact about the fixed point theory. So as we know that there is no guarantee of the existence of a fixed point of a given map. So question is that under what condition one can have the guarantee of the existence of the fixed point. So in this connection I am going to discuss the first result on the existence and uniqueness of a fixed point. Okay, so this result is known as the Banach contraction principle. So this result was proved by the Polish mathematician Stefan Banach in 1922. And one interesting fact about the Banach, basically you can say initially he was a computer engineer, he was not a basically mathematician. So he did this theorem on the space of the continuous functions, means on C of AB. But later on people or other authors state his theorem as a simply as a general theorem. So what is this theorem? Banach contraction principle. In short, we can say BCP. So this is Banach fixed point theorem. So it's result from the 1922. So the statement of this result is simple. So let X be a complete metric space or you can say Banach space, because result is also true in Banach setting. So let X be a complete metric space and T be a self contraction on X is d of dx dy is less than equals to alpha times d of xy for all xy in X. Then we have these consequences of Banach contraction principle or Banach fixed point theorem. First of all, T has a fixed point. Means first of all we have a guarantee of fixed point of map T has a fixed point. Second consequence of this result, fixed point is unique. Fixed point is unique because we know several examples there we don't have the uniqueness of the fixed point. For example, identity map or maybe any polynomial function of degree more than 1. And we have basically third consequence of this result. So suppose it has a point, you can say X or maybe Z. So suppose say X, okay, or X bar, you can take okay, Z. And if we consider the this sequence defined by the sequence defined by this rule, xn plus 1 equals to txn. Okay, or this is same as tn x naught for some where x naught is some element of the x, and this sequence xn plus 1 converge to this fixed point Z as n has 2. So in the third part means we can say that we can also approximate the fixed point of the given contraction map T. So it has three consequences. One is the existence. So this is the first problem because we don't know we don't have the guarantee of the existence of the fixed point for a given map. But under this condition, if we have a contraction map which is defined on a complete metric space or Banach space, then it has at least one fixed point. But of course, due to this contraction, this fixed point is unique. And last one, if we consider this type of equation for any arbitrary x0, then such sequence is always converges to the fixed point of the given map T, contraction map. So proof of this theorem is difficult. So let us see the thing simple way. So proof So first of all, suppose x0 in X is an arbitrary element and now consider or you can construct the sequence. This sequence is called the iterative sequence. And another name is also called, this is the Picard sequence, or because given by the Picard sequence of iterates. So how we can consider this? We can construct the sequence like this. This is start with the point x0. Then we have its image is tx0, but tx0 is denoted by this x1. Then again we apply the t over the x1. So t over the x1 like this, and this is called simply x2, but t of x1, but x1 is t of x0, so this is t of x0 equals to t square x0. So we have the sequence like first element x0, then x1, x2 in this way, and similarly we can go x3 is image of the x2 and the t, but x2 is basically my t square x0, so this is t cube x0, and in this way we can define the sequence tn xn plus 1 equals to just we can say t of xn and t of xn we can put very simple way tn x. So that is my sequence is like this one. You can say x0 tx0 t square x0 x0, and this is simple. Or we can say this is x0, x1, x2, x3, and in this way just xn plus 1. Okay, so of course my n is set of positive integer. So my first claim is that the sequence constructed in this step is a basically Cauchy sequence in X. So my claim is that the sequence xn or xn plus 1 doesn't matter is a Cauchy sequence in X. Okay, so for this we will do some calculation. So just start or consider this step d of you can say xn plus 1 and xn. Just we are going to calculate the distance between the two consecutive terms of the sequence, and which is same as d of what is my sequence? You can say xn plus 1 equals to txn, and xn will be txn minus. But my t is a contraction, so that's why by the definition of contraction, this is less than equals to alpha times d of xn and xn minus 1. Okay, and again for the xn I can write this is simply t xn minus 1, and for this term x of n minus 1 is same as the t of xn minus 2. So maybe here I can write times this is d of t xn minus 1 and this is t of xn minus 2. But since this t is a contraction, so that's why this is again less than equals to alpha times again alpha, so this is alpha square d of xn minus 1 and xn minus 2. And in this way we can go ahead and finally we will get this type of thing. So this is just less than equals to alpha to the power n d of x1 x1. So in this way we just calculate the distance between these two consecutive terms of the sequence. Next, now we will prove that the sequence is a Cauchy sequence. So just start now. Consider this simple any integer m greater than n, and just consider d of this xn xn. So using the triangularity here we can write these terms this way. So just start less than equals to d of xn plus 1 plus d of xn plus 1 and plus 2 and just so on. And this is it goes up to the d of this you can say in simple way xn minus 1 and xn. And just using our this estimate here from the here, and we can write this is less than equals to alpha to the power n This you can see in the previous part, plus alpha to the power n plus 1 for this one, because this is d of xn plus 1 comma xn plus 2. So in this way we go plus alpha to the power n minus 1 and 4 common is d of x naught comma x, because this total quantity d of xn plus 1, xn is less than equals to alpha power n d of x naught x1. So just this is basically finite to see. So this is sum is, you can take common here. So this is alpha to the power n, and this is 1 minus m minus n over 1 minus alpha d of x naught by the geometric series. Okay, as my alpha, of course we know that. What is my alpha? Alpha is from the open interval 0, 1. So alpha to power m minus n is less than 1. So 1 minus this quantity, so this is also strictly less than equals to 1. So we can write this is also less than equals to alpha to the power n over 1 minus alpha d of x naught x1 as 1 minus alpha to the power m minus n is also less than. And now just consider the limit. N tends to infinity, so of course this part goes to, it means whenever we consider this n is very large, so it means that this part goes to 0. So this goes to 0 as n approaches to infinity. So that is this shows that the sequence defined by the Picardy traits, the sequence xn is Cauchy sequence. Okay, so now we have a Cauchy sequence in a complete metric space. Then it must have a limit, because we are working in the complete metric space or Banach space. So that's why it has a limit. So since x is a complete metric space, and xn is Cauchy, then xn has a limit in x. Has a limit in x. So say this limit is z. So that is xn converges to z as n goes to approaches to infinity. So in some sense, of course, if you see the things carefully, we proved the last part of the theorem. Means if we consider the Picard sequence or iterative sequence defined by the Picardy traits, then it's always converges to the fixed point of the map. So now we have to prove that this limit z is a basically fixed point of the operator t. So proof of this one is also a simple one, because the sequence was defined for the arbitrary point element x naught. So, okay, big issue. So xn converts to z. So just we will use the basic result of the. Of course, for this part means to prove that z is a fixed point of t. It's very elementary step to prove this one, but I will use the one basic result from the metric writing. So as xn converges to z, and we know that t is a contraction, so that's why it's a continuous map. T is a continuous over x. So, for means t of xn also converges to t of z. So we know that one result on the entropy from the pre-analysis of metric space, whenever we have a sequence xn converges to z, then t of xn also converges to its image z. Okay. But what is the t of xn? So t of xn is xn plus 1, or that is, this is same as this my txn is xn 1 plus 1 is equals to z, of course, as n tends to be. So now we can see, of course, this is xn converges to z, and this is the same sequence xn plus 1 also converges to the tz. So this is basically same sequence, just we add the one term. So is that we have the same sequence which is converging to the basically two elements z and tz, and of course in the metric space is always unique. So that's why. So this implies that this both limits should be both limits. Both limits will be same. That is